All right, it looks like people are rolling in. Sometimes it takes a second for um, my voice to get in your headphones, so I'm just kind of vamp here for a second. Um, our cameras will not work, so it is a very disembodied webinar for everyone today. But you have made it to our March 14th webinar, Commercial Heat Pump Water Heater System Considerations in a Nutshell with Evan, who you may have seen in a couple other um, webinars done for us. And then, he works for Ecotope, so you may have seen him present other places. So as everybody's rolling in, let me get started on the next screen and let you know how these webinars go. If you haven't taken one with us at the Lighting Design Lab before, um, go-to isn't, some system that everybody's used, even though it's the oldest one. Fun fact. So you're all going to be on mute this entire time, but there's this little questions icon up at the top of your menu bar. If you click that, a little window will pop out and you can ask questions there anytime. If we have anything to add, like a link or something, it'll be in the chat icon window, even though you won't be able to see each other's questions. Submit anytime. The webinar is being recorded. It's already started recording, and we will post that within about a week of the end of the webinar, along with the slide deck. And we have a little survey after the webinar, so be sure to take that, please, please, please. We are the Lighting Design Lab. If you have not heard of us, um, don't feel embarrassed. I hadn't before I worked for City Light. The Lighting Design Lab's been around for 30 years. It was a brainchild of BPA and the Northwest Utilities to expand the lighting market to the cutting edge fluorescent lights. But now we've expanded because it's not just lights in buildings anymore. We need to transform the market in all kinds of electrical building technologies. So that's what we are doing to support the city's goals. And we have a couple more events coming up. One more this month about very highly efficient, or there's another very high efficiency. I don't know which is, I've seen it both, dedicated outdoor air systems, also with Ecotope. And then Armando's team with Ted Brown from City Light are going to come talk about some controls incentives that City Light has going on here in April. And then we're going to do a cool presentation called the Carbonization Countdown, with some people from Mitsubishi Electric's Train US organization. And those are available to sign up on our website. But let's get started with a couple Slido questions. If you haven't used Slido before, you can scan that barcode with your phone or type in slido.com on if you've got another monitor that you're using. Over on the other monitor, there's the entry code 7948864, and then once you get in there, it'll ask you for a passcode, and that is TSXCJW. And I'll give you guys a second to get in there. And here's our first question. It's super easy. Where do you do most of your work? Not necessarily where your office is, but the buildings you work on or design for, where is that work located? And we've got participation. Yay. This is great. Okay. 7, 8 people. Well, we've got more attendees than that. I'll give people a second to get into Slido. That little, find my cursor here. There's the entry stuff to get in if you missed that first slide. Great. Okay. Looks like mostly in our area. Evan, our presenter, I learned is in Eastern Washington today, on top of a mountain. Okay, and now the next question is the most important because it is March 14th, 3.14, Pi Day. What's the best kind of pie? Um, and once we get that answered, I will hand it over to Evan to get the real the real content going. I think nobody's answering this question. I can't believe it.
Hey, I'll chime in here, Katie.
Okay,
This
okay.
yeah, my favorite kind of pie is definitely blackberry.
Ooh,
I think
yeah.
yeah, I think you have to advance one more to let them answer the question. I don't see it on my
Okay. Let me
potential.
butterscotch pecan cream, says Robert. Nope. It says that I need to start presenting, but I am presenting, so I'm not real sure what's going on. Well, for those of you that are answering this and it's not showing up, thank you for this information. All right, Evan, I'm going to hand it over to you. And where is your
Oh
make
yeah,
presenter? And you should have gotten the presenter link now. And just so that everybody knows, and especially because the Slido maybe is or isn't working, um, any questions you have now from now on, go ahead and ask in the questions window here at GoTo and not in that Slido. All right, I'm going to go off mic. Take it away, Evan.
okay. So I'm getting a curious message from GoTo right now that it does not feel like sharing my screen. Okay, great. It worked the second time.
I see it.
So
Yep, it's working.
great. GoTo's been a little interesting this morning. Yeah, thanks for that. Thanks for that intro, Katie. I can introduce myself. My name's Evan Green. I'm a research engineer at Ecotope. So we're a consulting engineering firm based out of Seattle, and we work in this cool intersection between design, research, and policy to with a mission to decarbonize buildings. So on the design side, we've been designing around these commercial heat pump water heating systems since back in 2010, around Colmax heat pump water heaters because they were the first in the market and started in Hawaii before we brought them over here and started putting them into Seattle buildings. And then we did a lot of monitoring on those first designs, and we've continued to do monitoring on these different plants to really better assess the efficiency of these systems overall. And then we use our monitoring to both feed back into our designs and improve those designs and to make sure we have really solid heat pump water heating system installations. But we also work with local governments and utilities to figure out the best way to get these systems implemented. So that's where our policy team comes in. So I get to wear many hats from design to research to policy and to education, and a lot of it centers around these commercial heat pump water heaters. So I've had a lot of fun with them. There's a lot to learn, and we've been able to work with a lot of manufacturers to try and try and get everyone on the same page about how these systems can be best implemented in these buildings. So this webinar today is an attempt to share that knowledge, share the lessons that we've learned, so then you don't have to learn these lessons the hard way like we did in the early 2010s. And I've been told there's a little bit of delay on the slide changes, so there might be a little bit of a pause as I go to change slides just to make sure that I'm not falling behind here. So what we're going to talk about today, we're going to cover what a CHPWH system is, or commercial heat pump water heating system. We're going to talk about why we would use these in our buildings today, and we'll talk about all the different components of these commercial water heating systems. And then finally, we'll talk about how to size them make sure you have the right size heat pump and storage to fit into your building and satisfy your loads. And then we'll bring that all together to talk about how to actually get this system into a building. What does the market flow look like to deliver these to the buildings? So I'll start by saying that when I'm talking about a commercial heat pump water heating system, I'm talking about more than the heat pump itself. So if we look at this picture here, we see a hot water plant that's located on a beautiful rooftop in California. And you see there's 6 heat pump water heaters here. But this is just a heat pump water heater. If we're talking about a heat pump water heating system, we're talking about all the components in the domestic hot water plant to actually be able to serve that hot water. So in this system, for example, we have these 6 heat pumps. We have 3 storage tanks over here on the right. And then hiding behind them, there's an electric water heater for temperature maintenance in this big silver box. And then hiding behind that is a heat pump. So the heat pump in the back is heating that hot water circulation loop. We'll get into deeper on how that works in a little while here. And then the electric water heater is just serving as redundancy as the last point of flow going into the building. And then on this rooftop, I should mention we have a few heat pumps scattered throughout here, and those are just for space conditioning and not related to the hot water. So heat pump water heater circled here in orange, and the heat pump water heating system is this entire hot water plant. And it's really important to think about these as entire systems because the heat pump is very efficient, but only if it has all of the other components to complement its operation. So as I talk about a lot of different definitions in this webinar, they all kind of anchor back to a central source that I'm really happy to be able to point to now, and that is NEA's Advanced Water Heating Specification. So NEA is the Northwest Energy Efficiency Alliance, and they've authored this Advanced Water Heating Specification to be able to really anchor the industry and make sure that everyone is going the same direction to help advance this technology as clearly and reliably as possible. So manufacturers tie into this specification through the qualified products list that I'll talk about on the next slide. Utilities are able to reference this spec as they build incentive programs, and designers can reference this spec and look at the products that comply with this specification, knowing that these are very solid designs that this specification references because all the designs in this specification have been proven both in the field and in lab testing over the last 10 years. And finally, there's quite a few codes that are now referencing the advanced water heating specification because there's one level of code where you could say we need to install heat pump water heaters, but we as a we as a society also want our water heating systems to work really reliably. So um, you can reference this standard to be able to reference these systems that are very reliable and proven out. So the qualified products list is a way to bring the manufacturers into the specification and show that they've complied with the standards that the advanced water heating spec sets. So one standard, for example, is to promote a specified piping configuration, and we'll go through these configurations throughout this webinar. But also there are different things like warranty requirements and different communications that should be complied with as a manufacturer on this spec. So the qualified products list is a list of manufacturers that are compliant with this spec, but it actually takes it a step further because we're taking climate zone and system piping configuration and equipment level performance into account to model a full annual system efficiency, or we'll call it system COP, which I'll explain exactly what that means as well. But here we have an example, and this isn't the entire list, but this is just a screenshot of part of the qualified products list, where we have the company supplying the product, we have the product model, and the configuration, the piping configuration that this should be piped in. So if you're a designer or an implementer, you want to make sure that the design conforms with this configuration that the manufacturer is recommending. And we also have a market delivery method that we'll explain later here as well. So all of these together uh, will really define how the system performs. And so we'll take annual weather data in several different climates, as you can see in these ASHRAE climate zones up here, and we'll model the system in these specific configurations using those heat pump water heater performance maps to come up with the efficiency of the entire system, not just the heat pump. And then we will assign a tier level to that NIA has put together. So you can see there's 4 different larger climate zones that we can categorize these systems into and how they perform. And as the tier level goes higher, we see a higher minimum system COP to be able to hit that tier level. So you'll see a lot of the products on the list here are just tier 1 or tier 2. But we want to make sure we're aggressive with this tier structure to make sure that as technology advances with these systems and as their efficiency climbs, there is a way to recognize those much higher efficient systems. So what makes the C in commercial heat pump water heater system? So there's residential heat pumps and there's also commercial heat pumps. So as we talk about a commercial water heating system, I already mentioned that it's not just the heat pumps, it's all of the heat pumps together with the tanks and the temperature maintenance heater. So we can look at the entire system to define this threshold of commercial. So commercial in the advanced water heating spec, which aligns with DOE's definitions, is if your system is 120 gallons or greater, or 6 kilowatts or more of input power. So the heat pumps you saw in the first image, those actually don't have 6 kilowatts input power for a single heat pump, but all 6 of them together require more than 6 kilowatts input power. So we have 6 residential grade heat pumps packaged together to create a commercial heat pump water heating system. So it's important to this is important because the systems are rated in different ways, whether they're residential or commercial. So what's important to realize here is we're talking about system size. We're not we're not actually talking about what the system serves, right? So a commercial system, for example, that rooftop system that I showed in the first picture, that's serving a residential load. It's a multifamily building, but it's a commercial heat pump water heating system. So residential in this context is just the size of the system. It's not actually the load that it's serving. So these commercial heat pump water heating systems, they can serve multifamily or they could serve, say, large kitchens or offices. It doesn't matter the building type. It's just commercial if it's above this 6 kilowatts input power and above the 120 gallon mark. So now that we've defined a commercial heat pump water heating system, let's talk about why we would actually want to put one in our building. So the first, of course, is energy savings. So these heat pump water heaters, they don't use electricity to create energy with these electric elements. They're actually harvesting energy from the air around them or some source that has heat in it. So they're harvesting heat from the air and transferring that into the water. So that's why they're able to operate with efficiencies much greater than 100%, or we rate them as a COP that I'll get into in a second here. But if we actually translate this into a real building, we'll use a multifamily building in Seattle, for example. Ecotope did a study quite a few years ago now to assess the breakdown of different loads in a multifamily building. And we found that about 25% of the total building's energy load is hot water heating. So with a heat pump water heater with an efficiency about 300% or a COP of 3, we'll see that we cut about 17% of the total building's energy usage by tackling that domestic hot water load with a heat pump water heater. So instead of 25% of that pie, we're cutting 17% off to drop that down to only 8%. And you can see this is broken down into temperature maintenance heating, which is our hot water circulation loop, and primary water heating. And I'll dive into that a little bit later as well. Aside from the energy usage, uh, point of use emissions are very important to consider in our cities. There are a lot of people in a very small space, and that means a lot of hot water that needs to be heated both for domestic water heating and for space conditioning. So if you're using natural gas to heat that water, then you have an exhaust pipe coming out of each one of these water heating plants, and then you have your local populations breathing that exhaust in. So heat pump water heaters, on the other hand, they're only the only byproduct from heat pump water heaters is clean water through condensate and cooler air, right? They harvest the heat from this air and just spit out cooler air, but it's just as clean as when it came in. And so this is really important, especially in urban areas, to be able to keep the air clean as possible and keep people nice and healthy. So if you're not incentivized by clean air and energy savings, there are also utility level incentives that are available for these water heating systems. So uh, there are custom incentives that you can pursue through any of your local utilities. You just have to talk to your energy manager at that utility. But one example from Seattle City Light is this retrofit incentive for heat pump water heating systems specifically. So we have 24 cents per kilowatt hour saved on an annual basis. And the measure note, you'll see it must meet NEA's advanced water heating specification. So that spec has already it's weaved into these incentive structures to make sure that not only are people installing efficient water heating systems, but they're installing them in a reliable way so we'll actually realize those savings. And we'll see if we're talking new construction, there's a pretty clear reason why you'll want to install heat pump water heaters, and that is the easiest way through code compliance. Right, I have the Seattle Energy Code on the left here, and the Washington State Energy Code, the 2021 Washington State Energy Code. So it's very close to being implemented now, and you can see in multifamily residential buildings, or R1 and R2 occupancies, they both require air source heat pump water heating for the primary means of domestic water heating. So it's really important to understand how these systems work, because any new construction in the future, the easiest pathway to compliance will be installing these heat pump water heating systems. And you see there's an exception in each of these codes have a pretty stringent design recommendation or design requirement to be able to implement these systems, and it's not super straightforward if you're just reading the code line by line on how that design actually works. But you'll see on each of these exceptions, as long as the system complies with this advanced water heating specification that I talked about, you are code compliant. So the code basically points to a swing tank system only to heat these domestic hot water plants, but the advanced water heating spec lists several configurations, which include a swing tank system, but it lists additional configurations that these manufacturers have recommended that you can install in your building as long as it's advanced water heating spec compliant. So now's a good time to check in. So we talked about what these systems are and why we would want to implement them. But I do want to hear back from all of you on any other reasons you might want to install heat pump water heating systems. What challenges have you been met with installing these if you've installed them before? And does this advanced water heating spec make sense? Is there Are there other places that it could fit in, or are there some more clarifications that should be made to make it easier?
And while we wait for people to answer those questions, Evan, we have a few questions that came in. Do you want to look at those, or do you want me to read them to you?
Yeah, I could read through these ones.
Cool.
Yeah, so one, let's see. Whoops, I'll get there. I promise. There we go. Okay. Are there any equivalent Canadian standards that are applicable? That's a good question, and I don't have the answer to that. I haven't done work in Canada, but that is a good one to follow up on. I know there are quite a few system installs in Vancouver, so they may have it would be great to see this standard expand into Canada because there's not anything specific to the US, I believe that would hinder that, but I'm not aware of Canadian standards right now. How does Seattle City Light calculate the kilowatt hour savings for fuel switching? Electrical load increase, but therms go down. Yeah, that's a really tricky one. I think you will. I wonder if Katie or Robert, if you might be able to find a link for the
Yeah.
energy manager to talk to.
Let me answer that really quickly. We don't. I'm not entirely sure, Bill, if you were hearing Evan talk about savings. He's not referencing any calculations City Light did. Um, Usually, if you were going to switch systems, you'd be working with City Light staff, several of which are on this call actually, and they do, calculations for you on your system. Um, but we don't put out any like here's and the yeah that's true. Robert was just reminding me there's no rebate for fuel switching, but calculating the kilowatt hour savings is going to be specific to your project.
Mhm. Yeah, and I know Bonneville Power is tackling that question as well. It is not very clean cut, so maybe it's
It's
still a to
not,
be
yeah.
determined as well. Ooh, I really like this. I really like this next question. It said, I know you stated the only byproducts are cooler air and condensate, but has Ecotope studied refrigeration loss through leaks or equipment breakdown? We I I think there is a study out. I'm not super privy to it, but there is a great distinction that this could point to between standalone heat pump water heaters or split systems and VRF systems, right? Or a variable refrigerant flow. So these VRF systems send refrigerant through the entire building, and so we're talking about a lot of refrigerant to handle this space conditioning and a lot of potential leak points that are field installed while while commercial heat pump water heater manufacturers, we're talking about packaged equipment on the roof or outside that is much lower refrigerant charge. So there definitely are still leaks. They're a lot lower than something like a VRF system, but they are still there. So that brings into question the importance of natural refrigerants like CO2 or even propane, which isn't currently allowed right now. It's important that we don't let too many of these synthetic refrigerants out into our atmosphere because that could cause some major changes. So leakage is an issue that we should tackle, and natural refrigerants are a great way to tackle that because if you have a CO2 system with 5 pounds of CO2 charge, it's a lot less of a big deal if that leaks out once or twice in the equipment's lifetime as these higher GWP refrigerants that we'll get into a little bit later. Okay. Okay, most common refrigerants used in these systems. Has Ecotope completed any systems that utilize CO2 as a refrigerant? So yes, we have done several Sand Code 2 systems with CO2 and a Mitsubishi, and there are a couple demonstration projects coming out from other manufacturers. So R134A was kind of the first go-to, saying that those in parking garages worked pretty darn well, but CO2 has been really great because you can just set it straight outside and it operates much lower than Seattle's min design temp. So you don't have to worry about any backup to satisfy those temps. And we'll get into refrigerants in a little bit here, but that was a good teaser.
And before you answer the next one, Bayview Tower, one that Ecotope helped work on, um, did a CO2 heat pump there in Bayview Tower, and some of your colleagues came on and did a webinar about that. I put the link to that in the chat if you guys want to view that at any other time.
Perfect. Yeah, thanks, Katie. That was a great demonstration of both CO2 and fully packaged systems that we'll get into. And another question, is there a max temp that these systems are capable of heating to? And is it influenced by the temp of inflow water? And the answer is yes, and I think we'll get into that in the refrigerant section as well. And then, yeah, there's quite a few more questions here. So maybe I'll tackle one more question, and that is how often are you seeing compressor failures or control board issues or undercharged units? Says I see this far too often on the residential unitary heat pumps. So yeah, I think there have definitely been equipment level issues that need to be tackled as there's several smaller manufacturers trying to get a hold of these domestic hot water heat pumps. So I believe that this is going to be an economy of scale issue where if manufacturers have more resources to put into the manufacturing of these units, then we're going to see a lot fewer issues with control boards and compressor failures and things like that. Especially as the systems are standardized, we'll see a lot more beneficial conditions going to the heat pumps. And as manufacturing is as scaled up as we've seen in some of these larger manufacturers, we'll see a lot fewer failures that way. So there definitely have been failures on the commercial side, and I'm optimistic though that you'll see those taper off as these grow in market share. So these manufacturers have more resources to scale up. And these are all really great questions. I'm really happy with how many people have joined and how many questions are coming in because these two-way conversations are a lot more interesting for me and I'm sure for Katie and Robert too to be able to make this a more interactive conversation.
Yeah, absolutely. Keep them coming, guys.
Yeah. Okay, so now I like the kinds of questions that I've been getting because I like to dive into the technical weeds, and there are a few weeds that I think people are coming out of here today as well. So now is now is for you all to put on your engineering hats, and we can dive into the nuts and bolts of these systems and how they actually work. So we'll talk about the system components. And those are the heat pump water heater, the storage tanks, the temperature maintenance system, and the controls that bring it all together. And then we'll talk about system sizing, and we'll talk about market delivery. That should be a bullet point right here. Um, and then in the middle of that, we'll grab a coffee break so everyone can everyone can absorb what they've learned and then be ready to dive back in. Okay, so here's a cartoon version of the heat pump water heating system that I pictured at the beginning of the presentation, and I'll walk through the different components and how they function here. So we have our primary heat pump water heaters, which are the first thing you think of with a heat pump water heating system. Of course, they're the they're the heart of the system that will make very efficient hot water by harvesting heat from that air. And equally as important, though, is all of these other components that make sure that these heat pump water heaters see the conditions that they need to operate reliably and efficiently, right? So we have our primary storage tank is directly paired with our primary heat pump water heaters, and that storage tank is going to both supply really high peak hot water loads when everyone decides to get in a shower or do their dishes in the evening, but also it's going to make sure that these heat pumps are seeing the consistent and cool conditions, say consistent and cool inlet water temperatures that they really like to see to operate reliably. And it's going to make sure that there's a really solid buffer to be able to both supply a consistent outlet temperature to the system and bring in a consistent cold water temperature. And this buffer or hydraulic separation will also it'll buffer any big pressure spikes in the system that you see as people are opening and closing taps. So we have our primary system that is heating the domestic hot water for people to actually use. And then we have our temperature maintenance system over here that is heating the hot water circulation loop in the building that we'll dive into a little bit deeper, but it's making sure that all the pipes stay hot throughout the day, even if there's no hot water usage. So in this version of the system, we have both a temperature maintenance tank and a temperature maintenance heat pump water heater. So these are dedicated this is a dedicated system that can handle this warm return water really well, which is especially important when we're dealing with primary heat pump water heaters that can only heat really cold water efficiently. And then finally, we have these controls that will tie all of these system components together. It'll look at temperatures in various places, and it will tell the heat pumps when to turn on and off based off those temperatures to make sure that our system's sufficiently charged throughout the day. So diving into the primary heat pump water heater itself, I mentioned this is the heart of the system. So we're going to talk about the different types of primary heat pumps that you'll see out there on a commercial scale. We'll talk about how their performance is rated and what you need to consider if you're looking at the performance of that heat pump. And then we'll talk about refrigerants, which we've already had a couple really good questions about. So there are three main types of heat pump water heaters that we'll see installed in commercial buildings. So first is a single pass heat pump water heater. And you'll notice that this looks exactly like the multi-pass heat pump, but I'll talk about the difference. And then we have the integrated heat pump water heater where we have the heat pump and the storage and the backup electric element all tied into the same unit. So this integrated unit is a lot like those residential heat pumps that you'll see at the big box stores that you can just put in your basement as a replacement to an electric resistance heater, while these single pass and multi-pass systems are dedicated heat pumps split out from their storage tanks and other components to be able to just sit outside in most cases and provide that hot water to the building. So the difference between the flow in single pass and multi-pass here is really important. And the first thing I want to point to is the different coloring you'll see in these tanks, right? In the single pass system, you see that we have this nice big volume of hot water in red here. We have this small layer in yellow that we call the stratification layer, and then all the cold water is sitting in the bottom of the tank. So we have a stratified storage tank here, and the flow through the heat pump and the temperatures it produces is going to maintain this stratified storage. So we're actually, you can see there's nice cold water flowing into the heat pump, and we're actually throttling that flow through the heat pump water heater to be able to target a specific outlet water temperature. So we can always dump hot water into the top of this tank. So we're sucking cold water in, slowing that water down just enough to have enough time to heat up to the right storage temperature, and then we're dumping that hot water to the top of the tank. So we maintain this really clear stratified storage. And the one thing to consider with single pass that's unique to it is you do need specialized storage connections to be able to dump this hot water in the upper portion of the tank. Make sure that you're pulling from the bottom of the tank and then dumping back into the top. So a lot of standard storage tanks may not have this upper connection, so it's important to consider that in any designs. So the multi-pass heat pump, on the other hand, you see this yellow layer is a lot larger, and so this is sort of a mix of hot and cold water, and this tank's a lot more mixed because we have uncontrolled flow through this heat pump. Usually really high flow rates that will drive only about a 10-degree temperature difference through this heat pump. So you may be, on average, you might be sucking in 130-degree water into the bottom of this heat pump, and then you're returning 140-degree water into the tank to be able to heat it up to set point temperature. And so dumping heat into much colder water is a lot easier for a heat pump, so we're generally going to see a lot higher efficiency through these single pass heat pump water heaters because we're moving heat from 150-degree refrigerant into 60-degree water in a lot of cases, so that heat flows really smoothly. While in the multi-pass heat pump, we need to bump that refrigerant temperature up because the hot water we're dumping that water into, we're dumping that heat into, is a lot harder to push heat into because it's already hot. So the advantage of multi-pass, though, is it's piped very similar to the gas water heating systems that people will be familiar with. It's just controlled oftentimes off a single temperature point, and it just mixes the tank up as it flows a lot of water through here at a small delta T. And then the integrated heat pump water heater, I mentioned that the heat pump and the storage is combined. So it actually has a heat exchanger wrapping around the tank in the lower portion of the tank. So it's just transferring heat directly into the bottom of this tank. It's not actually flowing water between a heat pump and a storage tank. So there you see a little bit more tank mixing or a little bit less defined stratification, a lot more like multi-pass units. And the other big difference in these integrated heat pumps is they come with this built-in electric resistance element in the upper portion of the tank. So you can see on this, we'll get into the storage drawdowns more in depth, but you have a much higher chance of this electric resistance element firing if you have high water loads in your building. So these integrated heat pumps are definitely the easiest to install because you just have a hot and cold water connection, but they do have potential for having much lower efficiency if they're not sized really carefully, which is really hard to do because we have proprietary temperature set points inside these units that make it really tricky to design around. Okay, so now we can get into how this stratified storage actually works and is recharged by these heat pump water heaters. So starting with a single pass heat pump water heater, we start with this nice stratified storage tank, right? We have hot water filling most of the tank. So this is around 140, 150 degrees. And then we have warm to cold water at the very bottom where the cold water comes in. So if we imagine that we're beginning the day with this fully charged hot water storage tank, and then the morning hot water peak comes. A lot of people get out of bed and get in the shower. Then we're going to have a lot of hot water leaving the tank going to the building, and we'll have cold makeup water coming into the bottom through the sidewall of the storage tank here. So as this hot water draws out the top, we have cold makeup water filling the tank from the bottom up. And then as soon as that cold water reaches this temperature sensor that's attached to the heat pump, that temperature sensor sees that cold water there and knows that it's time to try and recharge that tank. So as soon as that temp sensor goes cold, your heat pump will turn on. It'll suck cold water from the bottom of the tank, and it'll return hot water to the top of the tank. So these heat pumps have relatively low recovery though, which means we need to pair with sufficient hot water storage. And what that means is if everyone's taking their morning shower, you have your peak usage period during the day or during the morning, then our heat pump's running to try and recharge this tank, but people are using hot water more quickly than the heat pump can actually generate it. So the storage tank will continue to draw down. See the hot water being pulled from the top of the tank, cold water makeup coming in the bottom. And then the heat pump is essentially directly contributing to that load in parallel with the storage contributing. So the heat pump can't keep up with this peak load on its own, but it has this storage to be able to supply the extra water in that peak load. And then it needs to be sized in a way that this storage will not run out before that peak period subsides. So we'll get into that with our sizing at the end of the webinar today. Okay, and then finally, let's imagine that people have gotten out of the showers. Most of the people in the building are on their way to work or working from home in my case, but ready for work and ready to go. Now the heat pump can keep up with the load, and it can make more hot water than the building needs. So now it's going to recharge this storage tank, suck all the hot water, suck all the cold water from the bottom, and push all the hot water back into the storage tank to charge it from the top down. So here you see, like in most stratified storage tanks, we see a nice cold section on the bottom and hot section on top. But really at the very end of this run period, the heat pump's going to notice that the bottom of the tank is now warm because it has fully charged this tank. So as soon as that bottom of tank goes warm, say 120 degrees or so, and the heat pump starts sucking in that 120 degree water, it knows the tank's completely full and it can shut back off. Okay, so multi-pass operation has a couple of these steps are exactly the same. So I've shown the 4 steps where we start with a completely charged storage tank, heat pumps off and ready to go. Then the building starts using a lot of hot water. So we still have cold water drawing the bottom, hot water being sucked out of the top of the tank. But the key difference here in a multi-pass heat pump, as soon as this sensor starts seeing cold water, then we'll move to this next stage where the heat pump starts to run, and the high flow from this heat pump and really low temperature delta will actually mix the warm and cold water as the tank draws down. So now we have maybe 100, 110, 115 degree water mixed in the bottom portion of this tank. We still have a pretty good hot water layer on top, but this tank actually has a lot less energy to give before the occupants start seeing cold water again. Because you can see this, if this tank's being mixed to 110 degrees or so, because this heat pump is flowing really small delta T, we're actually not creating hot water that can be instantly used by the building. So this tank can draw all the way down, and then by the time this entire tank's yellow in this case, then people start seeing tepid water or lukewarm water that they're not going to be very happy to shower with. So this tank hasn't been able to draw down to 60 degrees it's only been able to draw down to about 110 degrees, right? 115 degrees before people start noticing. So there's a lot less available energy for this tank to give, and the heat pump's not able to directly supply that hot water to the building because it's mixing in to the rest of the storage tank. So that's where multipass really is less advantageous, is there's a lot less stored heating capacity that can be supplied in those peak usage periods. So you need a lot larger storage tanks to be able to supply the same peak load. And we've shown this in lab testing that that tepid water comes a lot more quickly than in single pass systems, even with a heat pump with the same capacity. So if your storage is sized properly though, then you'll still be able to serve hot water through that peak load. And then as that peak subsides, the heat pump capacity is higher than what the building needs, and it'll recharge this tank and make it hot again. And then so you can see too, as you go from step 3 to step 4, this entire volume of water is rising in temperature instead of sucking in cold water until the very end. So you have really high entering water temperature for a pretty long period as you recharge this storage tank. So the average entering temperature for these multi-pass heat pumps is much higher, which is driving a bit lower efficiency. Okay, so moving away from how they actually supply the hot water to the storage tank, now we can zoom out to the environmental conditions and the air that the heat pumps are actually harvesting the heat from to put into those tanks. So right here we're looking at an operating envelope for a heat pump water heater, and this operating envelope changes shape and size based on the manufacturer and, more importantly, the refrigerant of the heat pump. So definitely don't look at this envelope specifically if you're designing a heat pump water heating system. You'll want to ask the manufacturer for an envelope that looks like this. So we'll look at the four sides of this envelope to better understand the heat pump's capabilities. So we have the ambient air temperature on the x-axis here. You can see the air temps in this chart show 0 degrees to 110 degrees. We also have outlet water temperature. So this is the heat pump's outlet water temperature on the y-axis. And so what we're looking at here with this operating envelope, if we combine these x and y values, is, for example, at 20 degrees Fahrenheit ambient air temperature, we see a minimum outlet water temp that the heat pump needs to produce, which is less important for heat pump water heating design because we're trying to target 140 degrees usually. But we also see this maximum outlet water temp that the heat pump can produce. So you can see if we start really cold, the heat pump can only produce 110 degree water at its minimum operating temp. And then as the air warms up, it can produce much warmer water temperatures, right? By the time we get to 32 in this case, we're producing upwards above 160 degree water. And then it continuously warms as the air temp gets hotter and hotter. And then finally it flattens out in really high air temps. So the main takeaway here is if you see a heat pump water heater brochure that says it can operate down to 10 degrees, and somewhere else in the brochure says it can make 180 degree water, that doesn't mean it can make 180 degree water at 10 degrees. So if you're designing for Seattle around 26 degree outdoor air temp, then this heat pump in this example can make around 150 on the very edge of its operating envelope. I like to operate somewhere in here because this is the very edge, and you need really nice stable conditions to be able to run along the edge of this envelope. So yeah, it's really important to consider air temp in combination with outlet water temp, and you can reference envelopes like this from the manufacturer to get there. So the other two boundaries in this envelope that are really important is the minimum operating air temp and the max operating air temp. So the minimum temp in this example is about 5 degrees, and you can see the outlet water temperature is about 110 degrees there. And the maximum outlet temp is about 105 degrees. So if you're designing in really hot climates, then you should, if you see an envelope like this and your design temp is 118 degrees, then you should talk to the manufacturer and see if they have accommodated that with their heat pump. So yeah, in summary, definitely ask your manufacturer for an operating envelope like this, and then try to stay away from those borderlines if at all possible. Okay, so we've talked about how the heat pump charges the tank, what it can handle in terms of air, but now we can talk about how we actually rate these heat pumps and the systems they're a part of. So there's two things you'll see on an equipment schedule or on a brochure in a commercial heat pump water heater, and that is the capacity, which is how much heat is actually provided from the heat pump, and this changes with air temperatures we'll look at, and the coefficient of performance, which is the efficiency of the heat pump water heater. So the capacities you're going to see in BTUs per hour, kBTUs per hour is on the scale of 1,000. I've seen MBH from refrigerant contractors, which isn't actually isn't actually mega BTUs per hour. It's just 1,000 BTUs, and also kilowatts. So yeah, MBH may trip you up, but make sure you get clarification there. Um, and then the coefficient of performance, or the efficiency of these heat pumps. You'll notice most other electric appliances are just rated as an efficiency, which is a percentage below 100%, meaning you use more power than the heat that's provided. But when we talk about coefficient of performance, since we actually provide more heat than power consumption, we get numbers greater than 1. So the equation we'll look at for coefficient of performance is how much heat was provided divided by how much energy was consumed. So if our heat pump, say using easy numbers, if we have a COP of 2, that means that we will heat 2 kilowatts, we'll heat water with 2 kilowatts for every 1 kilowatt of energy consumed. And this COP will definitely change with air and water temperatures, and we'll take a look at some plots to show that. Okay, so here's a plot from an unnamed manufacturer for heat pump COP, or efficiency, coefficient of performance. So on the x-axis of this plot, we see inlet water temperature, and the y-axis we see a COP. And then each of these different lines show a COP at a different outlet or a different ambient air temperature. So you can see the warmest air temperature, 95, shows a range of COPs at the highest because it's easiest to harvest heat from air when that air has an abundant amount of heat in it. So as the air temperature gets colder, our range of COPs does drop pretty significantly. And the other factor in this plot, which I was glad to find a plot that had these two factors because usually they don't overlap in manufacturer's documentation, is the inlet water temperature does have an impact on COP of these heat pumps. So I mentioned that the single pass heat pumps tend to be more efficient because they bring in really cold water. Well, here's the quantification of that, right? As our inlet water temperature rises, say from 60 degrees to 100 degrees, we can see that coefficient of performance does drop off, and that is regardless of air temperature. We see the same trend no matter what the outdoor air temperature is. We see a drop in that coefficient of performance. And the important factor here is the slope of that line, or how quickly that COP drops, does depend on the refrigerant your heat pump uses. So CO2, for example, right around 80 to 90 degrees, we'll see this COP drop off pretty significantly with really warm inlet water temperatures. So we'll get into that in a second here as well. Okay, now looking at a heat pump capacity plot. So capacity is also very dependent on ambient air temp, and sometimes it's dependent on that inlet water temp as well. So this plot we're looking at here, this is also manufacturer supplied from a different manufacturer, and it shows air temp on the x-axis, capacity on the y-axis. Right, so we'll see then these plot capacity at different inlet water temperatures. So this is also a nice plot because it has inlet water temp and ambient temp on one plot. Right, so we can see starting at around negative 15 degrees, as our air temperature rises, our capacity will also rise because it's easier to pull heat out of that warm air, right? So in most heat pumps, we have higher efficiency and higher capacity as that outdoor air temperature rises. And so you see all of these lines trend pretty well up to about 40 degrees. But the interesting thing in this plot is you'll see this heat pump has a much higher capacity in warmer air temps if it has a really cool inlet water temp. Right? So if you see a capacity line with just a single assumed inlet water temp, you need to kind of probe the manufacturer and say, is this applicable to all inlet water temps, or is there a different curve I should be looking at for my warmer design water temp? Right? If we're in Southern California and our inlet water temp 75 degrees, we can only design around a peak capacity of around 135,000 BTUs. So if we're in Seattle, though, designing around that 26 degree mark, then even if our heat pump brochure says it has 170,000 BTU capacity, down at 26 degrees, we really only have 120,000 BTUs. So that's what you need to grab from this plot, is that capacity derate as the air gets colder outside. And so I mentioned the impact of inlet water temp on CO2 specifically, but a key takeaway here in both looking at capacity and COP is that those characteristics are very different depending on the refrigerant you use. So I'm not going to go through I'm not going to go through each of these cases, but if we look at the difference between R134A and CO2, we see those different things like inlet water temperature and outlet water temperature and ambient air temperature have a different impact on these heat pumps with these refrigerants. So that's really important to consider when you're choosing the configuration your heat pump will be installed in, say single pass versus multi-pass, or different temperature maintenance configurations we'll get into. And the other thing that I alluded to earlier is these refrigerants have very different global warming potentials. Right? So global warming potential is the ability of a refrigerant to hold heat in our atmosphere if it's released through, say, a leak in a heat pump water heater. So R134A, for example, it has a GWP of 1300, meaning this is a comparison against CO2 is how this is rated. So 1 pound of R134A refrigerant released into the atmosphere is equivalent to 1,300 pounds of CO2 released into the atmosphere. So that adds up really quickly if we have these small leaks from these heat pumps. Say a CO2 heat pump, on the other hand, of course, 1 pound of CO2 released from a heat pump is the same as 1 pound of CO2 being released into the atmosphere. So there are phase out periods for these higher GWP refrigerants because of this. And so you'll see across the board, R134A will be phased out by 2035. And in many jurisdictions, that's going to be a lot sooner based off more stringent requirements in jurisdictions because of the fact that there are heat pumps out there that are already readily available with these lower GWPs. So we've talked about capacity, but there's also defrost, right? So capacity does drop as air temperature drops. Heat pump capacity does because it's harder to pull heat from that air. Uh, but you also need to consider the fact that ice will build on these heat pump coils as the air gets cooler, right? The heat pump coil gets even colder than the outside air. So if the outside air is 40 to 45 degrees outside, water won't be freezing anywhere else, but the coil is colder than that air temp always. So it will actually build ice in above freezing temperatures. So it's important to consider that the heat pump has to stop and melt that ice from time to time to be able to keep harvesting heat from that air. So there's actually a D rate on top of these performance maps that I've been showing you to consider that defrost. Right, and there's a few different ways to perform that defrost cycle that are very manufacturer specific. So it's important to go to your manufacturer to make sure that they're considering that D rate in their performance values, whether it's part of the performance table they give you or if it's an additional D rate that you need to stack on top of it. So I've seen D rates from 20 to 50% from different manufacturers. So it is not something that should be overlooked in these performance tables. Okay, so now is a good time for a check-in. We probably have a lot of questions. There's a lot to absorb there. So we'll go ahead, we'll do a check-in and I'll I'll look through these questions and give you all a chance to drop some more questions in. But I think now is a great time to stop and take a coffee break or a bio break if you need, and then we can tackle some of these questions. So some check-in items before we go are any questions about the capacity and COP of these heat pumps? Have you seen any applications where multipass really shines? And are there any new promising refrigerants that you've seen out there that you think might take the industry? All right, so I'll give you all a 5 minute break. So it's 11:08 now. We will check back in at 11:13. Okay, I'm back. I hope everyone had a little bit of time to digest, maybe get a little coffee to get some get some brain pathways firing. And I've just been reading through the questions here, and there's a lot of good ones. I'm not sure if I'm going to be able to get to all of them, but I'll pick a few that stood out. Um, let's see. So one asked if having multiple thermocouples at different heights in the tank has been utilized on hot water storage tanks to optimize peak period operation. Yes. So I went through a kind of a simple example with my storage charging, but in that example, we had one thermocouple in the tank, and then we had the heat pump inlet water temperature being monitored to turn the heat pump off. So that's basically two. That's kind of the same as two tank mounted thermocouples, but we're getting the most out of that storage tank by turning off based off hot water return temperature to the heat pump. So multiple thermocouples are a good idea both for load shift and optimizing that storage volume. And manufacturers have different ways of strategizing with that. Okay. Yep. So I had another good question. Why am I even referencing R134A instead of 513A in comparison to CO2? So the market is definitely moving for an R134A replacement. The market is moving to 513A. Um, Honestly, I don't have as much confidence in the characteristics of 513A to just drop it as a replacement for 134A, just because these units are so new that I'm not exactly sure how those characteristics can be defined, right? So it is a replacement, so it's an assumption that the characteristics are very similar, but I haven't dove in deep enough personally to make that direct comparison. Right, and so the 134A was definitely just an example, and you should talk closely with your manufacturer to determine those operating envelopes and how those system COPs change based off those different conditions, as well as the capacity. Was constant hot water temperature assumed for the COP graph? That was yes. So that's both for the COP graph and the capacity graph. Those capacities may change with different hot water temperatures, but usually they don't change much. And let's see, another good one. There are so many good questions, it's hard to narrow them down, but I want to make sure that we get through our content. How efficient are tanks at holding on to their heat when the hot water isn't being used? Are there systems that stop heating at night for buildings where we know we won't need nighttime use? Yeah, that's a very important question when we start when we start considering all these storage tanks, right? So there definitely is heat loss. It's pretty darn low compared to the overall building usage. Like it's kind of in the noise if you're talking about monitoring. But we do like at Ecotope, we like to spec one level higher of insulation on all of our storage tanks to make sure that we're not losing that heat. Especially because when we're talking about these single pass heat pumps that really like heating cold water, if our tanks are losing heat to the point where that 140 to 150 degree water is no longer usable, then the heat pump has to reheat that. So it's really important to keep that water nice and hot and make sure it's hot all the way up until it's used so we don't have to reheat the same water twice. All right, so those were a few of the questions. There were a lot of other good ones, so sorry if I didn't get to yours. But maybe if you, for any in-depth stuff, maybe if you can reach out via email, then I'd be happy to have these types of conversations. Okay, so now we can dive into domestic hot water storage, which is really essential to make sure heat pumps operate the way they're supposed to. So we'll talk about the functions of the storage tank. We'll talk about the locations that the heat pump should connect to these tanks, and we'll talk about in series versus parallel storage. So there, you have one volume of water in a single storage tank, but it is kind of broken up into different uses, right? So I talked about sorry, excuse me. I talked about the hot water storage tank being able to supply the peak loads in the building. So that's the hot water that's been heated by the heat pump and stored in the tank to be able to satisfy those peak loads. And so we call that the running volume. That's all the storage that can be used to supply the building. And then the cycling volume is the volume below that running volume that is needed to make sure the heat pumps actually run long enough every time they turn on. Right? Heat pumps really don't like short cycling or turning on and off really frequently. So we need to make sure there's enough volume below this temperature sensor that the heat pump can take a while to suck all this cold water in and heat it up to temperature. Right? So we want to make sure that that is at least 10 or 15 minutes. And so the cycling volume can be calculated based off how long it takes the heat pump to heat that volume of water, and we need to make sure that that's at least 10 minutes, right? So ask your manufacturer more about the cycling volume and their minimum runtime requirements to make sure that you're hitting that for your heat pump. There's also this unusable volume below the heat pump water heater inlet. So as the cold water comes into this tank, say the entire tank is warm, that cold water is kind of going to sink to the bottom of this storage tank. So we're sucking cold water from here. If there's a significant volume below this heat pump inlet, then that volume of water is just going to stay cold because the heat pump's going to suck water from above it. It's not going to suck water from down here as it's bringing that water in. So we want to minimize this volume below these bottom connections. And some manufacturers even have a connection coming from the bottom of the tank to supply the heat pump, right? You just got to make sure you have a really solid Y strainer to get any sediment that's settled to the bottom of that tank if you go that route. So both the cycling volume and unusable volume, these are combined into what we call an aquistat fraction. So that's used in the sizing of this storage. And what the aquistat fraction is, it's what percentage of the tank is below this aquistat or temperature sensor, right? So if this sensor was halfway up this tank, half the volume in this tank is below the temperature sensor. So we can't rely on that volume to be hot when a peak hot water load occurs, right? Because the heat pump's not turning on until this cold water reaches this sensor. So the volume above it, the running volume, can be relied upon to be there when that peak usage starts. But anything below that is more for the heat pump to cycle with. So the aquistat fraction is how much of that cycling volume makes up the entire storage volume. So in simpler terms, what's this temperature sensor height compared to the height of the storage tank? If this height is 4 feet, storage tank is 8 feet, then we have a 4 foot divided by 8 foot, meaning our aquistat fraction is 50%. So what percentage of the total tank volume is below this temperature sensor? And then the drawdown percent is the drawdown percentage or effective storage capacity, as it's also been called, is how much of this storage tank is usable, right? That is for either cycling volume or running volume. And so we figure that out by figuring out how much unusable storage is in this tank. So that includes the volume this below this connection, as well as about 10% of the tank volume at the very end of your run. So the way I've broken this down is if you start with a drawdown percentage of about 90% to account for, the stratification layer, and maybe the water starts to, as the stratification layer reaches the top of the tank, you can't really use that water. So that means about 90% of your water is usable. You want to subtract this unusable volume from that 90%. So if this unusable volume is 10% of your tank, say uh, 6 inches out of a 5 foot total tank height, you're going to subtract that 10% from your 90% usable volume. So you'll get a drawdown percentage of 80%. So if you're just plugging into sizing software and you haven't specified tanks yet, you could probably just assume a drawdown percentage of around 80%, and then you can fine tune that based off these connection points, right? If you have really high heat pump connection and a lot of unusable storage, then you'll need to lower that drawdown percent or effective storage capacity in a single pass tank. So diving in a little more on these connection locations, I want to hit the importance at a high level for each of these locations. So we want our domestic hot water supply connection to be as high as possible on the tank. Usually these are already provided on the top of the tank, and that's just so we can get the most out of this storage volume before cold water starts hitting the outlet connection. If this outlet connection was here, about 2/3 of the way up the tank, then the cold water would only make its way to about here before we start seeing cold water in the building. And then this whole portion of hot water up here would be useless. So we want to get that hot water supply on the top of the tank. We want to get the heat pump hot connection as high as possible on that tank too, so then it can contribute directly to that hot water supply to the building. If the hot connection was down here, like in a multi-pass system, we would have a lot of mixing. We wouldn't have a nice hot water supply that can go straight to that outlet connection. Then we have the thermo well in the tank. So that's where the temperature sensor for the heat pump will go. We want to make sure that's high enough that we have plenty of water to cycle the heat pump with, but low enough that we have plenty of this running volume to supply the peak load. Right? So that's the aquastat fraction. Remember, if this was easy numbers, is if this was 3 feet up the tank in a 10-foot tank, then this would be 30% aquastat fraction. Okay, and the two cold connections, we want to have a cold water inlet to the tank to at a very low point in the tank to maximize this stratification. We don't want this mixing with hot water, and we want a heat pump connection that's equal height or lower than this cold water connection. Right? Remember, we want to minimize the amount of water below this heat pump connection, so then the heat pump can suck all that cold water out of the tank before it shuts off. And one other important point here is we do want separate dedicated connections for this heat pump water heater. Right? We don't want to tee them directly into these inlet or outlets, because this heat pump is seeing varying. There's a couple of reasons. This heat pump sees varying pump speeds or varying throttling to target this outlet water temp. So it changes the flow of water, which is changing pressures. And so if it's driving those pressure changes right here at the tank outlet, then if this is going to the mixing valve, then the mixing valve will see those pressure changes, and it'll cause unreliable mixing valve operation. The other thing is, this is not always perfect storage temperature. It does float up and down a bit. So if this is changing, especially when the heat pump first turns on, this line will probably be all cold because it's cooled down. So if the heat pump turns on and that's going straight to the mixing valve will see cold water that's cooled from those heat pump lines. So dedicated hot and cold connections are important to satisfy the really, really smooth temperature operation and to separate those pressure variations between the taps opening and closing and the heat pump ramping up and down. So now we can look at with heat pump water heating systems. This hasn't really been seen in gas, but in heat pump water heating systems, we've employed these in-series storage tanks, which are essentially a way to create this virtual tall single tank to maximize stratification. Right? So the coldest tank in this series is connected, the top of this tank is connected to the bottom of the hotter tank in series. So that's equivalent to one tall storage tank with this continuous stratification, right? As the tank draws down, maybe this tank fills completely with cold water. Cold water then will then make its way to the bottom of this tank. And so you can see that, you can picture that with this tall tank where cold water coming in just works its way all the way up the tank as the hot water is drawn out the top. So parallel storage tanks, on the other hand, we can think of those as just one very wide storage tank, right? We don't have that really tall tank for stratification, but we have a really wide tank. So we have much lower flow velocity through this tank, but we just have this really wide stratification layer. So in this tank, as the hot water draws out, this stratification layer will move really slowly up or down the tank as there's a really wide cross section for it to move through. So then looking at these tanks side by side, there are some advantages and disadvantages of each option, right? The parallel tanks on the left versus the in-series tanks on the right. So you can see that on the parallel tanks, we have our cold water makeup, it splits before it enters each tank. So we actually have half the water flow going through each tank, meaning we have a much lower flow velocity through each tank. So that's going to drive a more stratified storage tank because we have lower flow through those tanks. And it's going to drive a lower pressure drop because we have half the water flow going through each of these connections and half the water flow going through each of these pipes. So the question is, we've kind of just started exploring this with recent lab data, is these parallel tanks may actually have higher effective storage capacity because of those lower flow velocities, right? So if water's flowing really slow and smoothly through these tanks, then this layer between hot and cold is not going to mix very much. It's going to stay really skinny. So we'll have more hot water to use for the building. The potential issue with these parallel storage tanks has to do with balancing the tanks. If these pipes are out of balance and you have high flows going to the building, then you might have more cold water entering one tank than you have entering the other one, right? So as these draw down, one tank may draw down more quickly, so it could go cold more quickly than the other tank does. And so that imbalance is really important to combat through really balanced piping. So you can see in this configuration, we have reverse return piping. So looking at the hot water supply, for example, we have a really short hot water supply line from the second tank, but that's the longest cold water supply line. So we have balanced piping to balance out those pressure drops so they draw down at the same rate. Something really interesting we saw in lab testing, though, is even if these tanks do become unbalanced, say if you could picture this tank being completely hot and this tank being halfway drawn down, once that draw subsides, once hot water usage slows down, those tanks will actually rebalance themselves because the hotter tank all this hot water is more buoyant. So it floats to the top of the tank and actually backfeeds into the second tank as cold water sinks to the bottom of this other tank, this first tank. So they'll become unbalanced during high draw periods, but then they'll rebalance themselves during low draw periods. So that it's still really important to keep your piping balanced, but it's not an imbalance that's going to accumulate over several days. So the in series tanks, the advantage that they do have the higher pressure drop because we have all the flow going through each tank, but there's more sensing granularity in these tanks. Say this, I mentioned how only half the flow is going through each tank, so these stratification layers move really slowly up the tanks in the parallel tanks. This stratification layer moves pretty quickly up these storage tanks. So if you have a temperature sensor in the bottom of each tank, you can sense that the tanks, say if they're at the bottom, you can sense that once this temperature sensor in the second tank goes cold, you can sense that half your storage is gone, right? If you have two sensors in each tank, you can tell when a quarter of your storage is gone, half is gone, three quarters is gone, and you can be a lot more granular if you're doing things like load shifting, right? So not really something to worry about if you're talking about a basic system, but once you start getting into load shifting, and you have to consider the number of sensors that are going to be in your tank to sense how much storage is actually remaining in those tanks, right? If you have one sensor in each of these storage tanks on the left in parallel storage, we only have one sensing point across this virtually very wide tank, right? So you need a lot more sensors. Isn't You need a lot more sensors in these parallel tanks to be able to have that granularity of sensing how much storage is remaining. Okay, now's a good time for a check-in. I hope I didn't lose too many people in the weeds there as I start talking about tank sensors and stratification layers. But this is a good time to check in and review any questions that have come in.
We have a lot, and people are still hanging in with you. No shade to your content, but I'm pretty sure it's because I asked people what their favorite kind of pie was.
Yeah, that's probably it. That really got the conversation started. I appreciate that, Katie. Okay. Okay, why can't oh, this is a good one. I Okay, why can't you have direct inlet water directly to the heat pump? Um, so that's a comment on my that's a question on the comment that you need dedicated inlet and outlet water connections for the heat pump water heater. So the reason that you don't want to have there's two reasons that you don't want to have your heat pump cold water line directly connected to the cold water makeup line from the city. And that is if at the end of run conditions, your heat pump, say your storage tank is almost completely warm, that means your heat pump starts to suck in relatively warm water. And that warm water is going to be pulled backwards through that cold water line and into the heat pump. Maybe I'll actually go back to that slide to here we go. Okay, so if your cold water line to the heat pump is actually tied into this cold city water line, if your tank's almost full of hot water and your heat pump's going to shut off pretty soon, then you're sucking, say, 110 to 120 degree water out of the tank and into your heat pump. But then if a few showers are started, or in a small building, if one tap is opened, that's when cold water from the city will flow into this tank to satisfy that hot water load. So this heat pump inlet then will go from 110 to 120 degrees, and then it will drop down to cold water temp if that flows high enough. So that's really hard on the heat pump, and it's hard for that as these heat pumps like really stable conditions, so it's really hard for it to respond to with this changing temperature as hot water flow changes, which means cold inlet water flow changes as well. So having a buffer temperature at the bottom of this tank will make sure the temperature entering the heat pump is a lot smoother and allow it more stable operation. So that also applies to the pressures in the system. If you have, as soon as you have a hot water tap open, that's when the pressure in this system, pressure in the hot water tap drops, and you'll have cold water rushing in. That stays pretty consistent pressure, right? So you have this big pressure change entering the heat pump as water starts flowing through this cold water line, and it's hard for the heat pump to respond to that in terms of its pump controls. So you want to decouple this from the cold water supply line to make sure you have this nice smooth buffer temperature both on the cold side of the heat pump and on the hot side. Okay, so that was a really great question. Has water quality or bacteria, i.e. Legionella, been studied for parallel versus series hot water storage tank configurations? That I haven't seen studies specific to in-series storage, but I would be interested because there is, say, in in-series storage tanks, there is, let's see if I can, say if you have pretty low usage, you have that surface heat loss that someone mentioned. You may have water that cools down in this tank and kind of drops to the bottom of this tank. So you may have below 140 in these in-series storage tanks if you're not consistently using your water, or if you're not doing like a return to primary. So they are studies that are worth having for sure, but I haven't seen any specific to these tanks or these configurations. Maybe we can tackle one more. Okay, yeah, there's a question about, is there any benefit to adding balancing valves to the inlets of parallel hot water storage tanks? That does get really tricky because usually those are pretty restricting overall. So you're increasing pressure drop through the plant, which you kind of want to avoid to be able to. Sorry, I'm making you swim here through different slides, but say if you have flow control on these inlet lines to balance those tanks, then you're introducing more pressure drop there. And also, if you're adding like constant balancing valves that aren't automatic, then one balancing valve setting will not provide sufficient balancing for the entire range of flow, right? So there are constant flow balancing valves, but they would introduce pretty high pressure drop. So I think as long as you have if you have reverse return piping or maybe even a bullhead T that goes to these, then you don't really have to worry about the additional balancing, because as I said, if they're a tiny bit imbalanced, then they'll rebalance themselves during low flow periods. And if you have reverse return, then they're pretty well balanced anyways. So, oops, I went too far. Okay, so I'll get going on some more content here. But those are awesome questions, and a little bummed I can't tackle all of them because they're all really good questions, but I was glad I could highlight a few. So now we talked about the primary storage and the heat pump and how that's charged and discharged, different storage configurations. Now we can talk about the temperature maintenance system, which has been a pretty big challenge for a lot of heat pump water heaters, because we really need to keep this entire distribution loop hot, so then everyone always has hot water access to these taps. But some of these heat pumps really don't like warm inlet water temperatures, right? So this warm water coming back from the recirc loop definitely warms up the bottom of this tank and causes a challenge for a lot of heat pumps. So we'll start we'll start with the simplest system that where the heat pumps can handle these high inlet water temps with a return to primary configuration. And then we'll talk about different temperature maintenance configurations to keep this heat pump inlet water nice and cool. So the return to primary configuration is probably what you would be most familiar with if you're familiar with gas water heating equipment, right? You don't have any extra temperature maintenance equipment, or by temperature maintenance heating, I mean hot water circulation heating. You don't have any additional temperature maintenance equipment. All of your water is just returning to the bottom of this tank, right? So when you're designing these systems, you got to think about the worst case scenario where you won't have any hot water usage overnight, and you'll just have a lot of this warm water entering the bottom of your tank, right? So if you're supplying 125-degree water, you may bring back 115 to 120 to the bottom of this tank. So your heat pump needs to be able to efficiently heat that 115 to 120 degree water. And it also needs to be set up so this temperature sensor will actually sense that slightly cooler water, right? Some set points we've seen have been as low as 100 to 110 degrees to turn this heat pump on. And that works fine if you have really well stratified storage without this recirc, but you need to assume that this tank may only cool to 120 degrees. So you may want to turn this sensor, you may want to trigger this heat pump on when this sensor reaches 125, right? And that means the heat pump won't turn off until that return temperature exceeds 130. So if that heat pump can handle those temperatures through the entire operating envelope, then this is certainly the simplest system. And if the heat pump can do that efficiently, it's going to be the most efficient and cost effective system out there. But you need to be really clear with your manufacturer that they need to handle these really high entering water temperatures and do so efficiently. So the cons of this system, of course, is if the heat pump can't handle those high temperatures, then it's going to either be really inefficient or just alarm out and supply cold water. So some CO2 heat pumps, for example, just cannot handle that high inlet water temp, and their controls are confined to lower set point temperatures, so they can't operate in this return to primary system. So if our solution to handling those high inlet temps is to break out the temperature maintenance system. So the only thing this primary heat pump sees is cold entering water, right? So in this system, with a parallel loop tank system, we have a dedicated heat pump and storage tank to reheat all of that hot water returning to the plant. So of course, this heat pump needs to be able to handle those high inlet water temperatures efficiently and reliably throughout the entire air temperature envelope, but it can be a lot smaller. And while this primary heat pump handles the entire domestic hot water usage load. So all the hot water that's going to the building or leaving fixtures will come through this primary storage tank, and this primary heat pump will heat it, while all the recirc water will come back to this temperature maintenance tank and be reheated by this heat pump on the right. And here you can see they actually do both of these hot water routes pass through this temperature maintenance tank. And in the parallel configuration, it passes through the very top. And the reason that we don't just go straight to the mixing valve with this is this primary temperature will not always be the same exact temperature as this temperature maintenance tank. So if they were teed in up here, then we have these temperature variations as fixtures are opened and closed, and the mixing valve is going to freak out a little bit when it sees that. So it's important to provide that buffer volume, so then we have a nice smooth water temperature going into the mixing valve. So this operation is most ideal if you're dealing with buildings, say old buildings with really high temperature maintenance losses or hot water circulation heat loss. But its con is it is more complex and higher cost because it has this additional temperature maintenance equipment. Okay, and so the other temperature maintenance system we'll talk about is the swing tank configuration. So this is the configuration that is probably most reliable for all heat pump manufacturers and especially for CO2 manufacturers because the primary heat pump will only see cold water and the temperature maintenance losses are handled partially just by an electric resistance heater, which is really, really reliable and pretty low maintenance and pretty cost effective as well. So the really cool thing about this system though is you'll see even though the primary heat pump it only sees cold water, it's handling the primary usage. You can see it passes through its hot water passes through the bottom of this temperature maintenance tank. So any water leaving a tap in this building has to come from the primary storage and travel all the way through this temperature maintenance tank before it gets sent to the building. And what that does is it actually uses this very efficiently heated primary storage to heat this temperature maintenance tank as it passes through. So this electric resistance element only needs to be used if we don't have water coming from the primary storage, meaning we don't have any hot water usage from the building. So during daily usage, especially if hot water circ losses are low, this electric resistance element actually won't turn on because we're getting all of our temperature maintenance heating from this primary flow. So we're reheating this warm return water, even though this heat pump that is providing the heat ultimately for it is only seeing cold entering water. So the downside to this, of course, is as soon as that hot water usage stops, we don't get any more flow from the primary system, right? We only have this recirc flow, so this tank will cool down. Right? As soon as this tank cools down, we have to heat it with electric resistance or other means of heating to maintain that temperature. So this system is really ideal for either buildings with pretty consistent usage throughout the day or buildings that can say if you can turn your hot water loop off outside of operating hours, like for an office building, for example, or if you have very low hot water circulation losses. Say you have a new construction building that has pretty stringent commissioning on the hot water distribution piping. Then finally we have the non-centralized systems. Right? So these are good because you don't actually have a distribution loop that needs to be circulated, so you don't have those temperature maintenance losses, but you do have the need for a lot more heating equipment because your heater needs to be extremely close to all the fixtures it's serving to not require that temperature maintenance loop. So you'll see this in multifamily buildings where there's clusters of dwelling units that are each served by say one of these larger integrated heaters. But you need to make sure that if you're going that route that each heater has its own source of fresh supply air and it's very close to each one of these fixtures. So it's a little bit higher cost potentially because you have a lot more heating, but there's less temperature maintenance loss and less heat loss throughout the system because those heaters are placed close to the fixtures. So it might work for some buildings, but not all buildings. But it's a good option to consider. Okay, and we're a little tight on time because there were a lot of great questions, and I'm kind of diving into the weeds here. So I'll see if I can pick one question out of the thread. And one good question. Are we going to get a copy of these slides? Oh, I see that Katie already answered.
I did, but I can let everybody else know too. Yeah, the slides and the recording will be available on, excuse me, Lighting Design Lab's website within about a week. Give me a week, and they'll be up there.
Great. Yeah, and there's a ton of content in these slides with the with the hope that they would be available to you all. So I didn't even hit all the content in some of these because they make a really great reference to go back to if you're, say, if you're talking to manufacturers or implementing these systems in a building. Okay. Okay, so the last component in these systems is controls. So controls are extremely important. They should not be overlooked because they're really the only thing that's going to make these heat pumps actually turn on and make hot water. So they need to be part of the scope and the contracting in these projects and part of the design up front. So we're going to talk about the key functions, the levels of control they supply, and a look at a sample sequence of operation here. So at a high level, the controls for these systems, they'll turn the equipment on and off to make sure that we stay charged up with hot water. They're going to monitor the equipment status. You can usually see on equipment screens how the equipment's doing. And it's important that they can send alarms if anything's not operating well. Some of these systems have electric resistance backup, so you won't actually notice if the heat pump's not working. You'll just have a much higher energy bill at the end of the month. So there's some different levels of control here. I've pictured a central controller already where it's reading all the temperatures in the system separately and then telling the heat pumps to turn on and off based off those temperatures. But there's also most of the equipment today has onboard controls that can handle that on its own. So say a heat pump paired with a storage tank can just look at the tank temperature on its own using its own supplied temperature sensor. And then what can bring these systems together is a building management system that will actually it'll monitor the status of this equipment that's operating on its own, but it won't actually tell it what to do. So if any of this equipment goes into alarm, it can send that alarm to the building management system that's centrally monitored by the maintenance staff, or it can supply things like equipment status and outlet water temperature and key water temperatures throughout the system without requiring this building management system to handle the kind of intricate sequences that some of these heat pumps require. So here's a sample sequence of operation. I'm not going to go through all the sequences, but this is to demonstrate how important it is to actually think about each part of the system and how they operate together. So you don't just have your primary heat pump turning on and off. You also want to set temperatures for your different components, right? Your swing tank needs to be 125. You may have a backup water heater that needs to be controlled. Your mixing valve has to have a set point temperature. Your circ pump has to have a temperature, pressure, and you need monitoring or alarms requirements in your sequence of operation if you want your building staff to receive those crucial heat pump alarms. So the manufacturers of each component can supply these sequences, and you just need to make sure that they're all on the same document. So whatever contractor is installing the system and setting it up can have that for a solid reference. So I'll go ahead. I know we only have a couple minutes here, so I'll cruise through some final slides. Now I've talked about system sizing as I've talked about the storage throughout this presentation, but let's talk about the resources we have out there for this system sizing. So at a high level, we're going to want to make sure that our hot water storage tank can supply the peak load in partnership with the heat pump water heater throughout the day, right? So here we have an hourly usage pattern in blue. So morning showers, breakfast, and then we have dinner and dishes in the evening. And we need to make sure that our heat pump can supply enough hot water throughout the day to keep these storage tanks charged. But also the storage that you see in orange, the storage volume needs to be able to contribute to these peak loads and then be recharged before the next peak hits. So that's the high level logic behind sizing software that's already available. So you don't particularly need to understand that logic, but it's good to have a little bit of a background. So this usage profile, this blue line here, is really important um, to know how much storage you'll actually need. So if your multifamily buildings are probably the best known in current software, but if you're dealing with a different building, you need to make sure the software is accounting for that specific building type to be able to accommodate a different load profile that'll require different storage. And then these heat pumps in the software, they're sized to run about 16 hours a day on a worst case scenario to satisfy the entire day's building hot water usage. So the EcoSizer is a sizing software that many manufacturers now reference and is available as a free source online through this link down here, ecosizer.ecotope.com. So Ecotope has worked with several utilities at this point to and manufacturers to make a system sizing software specific to heat pump water heaters. So you can see we have several different building types that drive that load profile. We have different occupancy counts that'll drive how much hot water this heat pump needs to provide through that 16-hour day period. And we have water temperatures that'll drive how much storage is needed to to be able to store that water and supply it during those peak periods. So given all those inputs, we have output of tank volume and heating capacity and temperature maintenance requirements if they're needed in a dedicated temperature maintenance system. And we also have this slider that allows you to say change those ratios of storage and heat pump recovery. If your heat pumps are a bit larger than needed, then you might get away with less storage, and you can slide this slider to ride this curve of heating capacity and primary tank volume to satisfy that. Okay, so the EcoSizer has a lot of really great documentation. I'll wait till the end to get any questions to make sure if anyone has to drop off, we can get through this last part that really brings this all together. So now that we understand these systems, we can talk about how they're delivered to the market, and then you can be, if your head's been spinning through this presentation, then you can be a little bit more assured that you don't need to know each one of these topics very super specifically to have a successful system. So we have three market delivery methods to get these systems into buildings, right? We have the custom engineered systems where an engineer has to think about all the concepts that I've mentioned here in depth and select each component individually to come together into a system in a building. And then the contractor has to source each of those components from their different suppliers and install them all together. Right? Then we have a specified or built up system, which really is a single product supplier, provides you with all the design support, sizing, and products in a complete heat pump water heater system. So they'll supply the tanks, the swing tank if we have it, heat pumps and pumps, and provide you with design guidance to put all these products together. So then that really takes, if you're a new engineer or a new installer working with these systems, then that really takes the responsibility and puts it on the product supplier to make sure all these systems work together. And then finally, we have a packaged system where a manufacturer actually packages all the equipment together before it goes to site and ships the entire hot water system as a single package to the site. So in the custom engineered system, the engineer has to know every little specific and all the nuances that make heat pumps work well, and then has to review submittals very cautiously in case installers have submitted different equipment that may not work as the designer intended. So Ecotope's done a lot of custom engineered systems, and we've learned a lot of lessons that way. But I'm happy to see that there are specified systems and packaged systems that take that they fill that knowledge gap with product suppliers that are really well versed in all of the products going into these systems. right? So the product rep holds the keys to success in a specified built up system, while the skid manufacturer holds the keys to success in a package system, right? The installer really only needs to know where to hook up the hot and cold water lines, and the designer only needs to know the envelope things like dimensions and how much water flow will have to flow through these systems. So here are some questions that you can go through as you're talking to your manufacturers about different systems. So the first set of questions have to do with compliance with the advanced water heating spec to make sure that they're pushing reliable systems that are really industry aligned. And then it talks about temperature maintenance configurations that are really important, and as well, and then closes out with questions on warranty and startup. And it's also important to make sure the manufacturer or rep has working systems in their area that they've demonstrated, because there's a lot of little wrinkles that need to be ironed out. And when a new heat pump comes online, or a new manufacturer puts one of these package systems together, so it's some engineers are less comfortable being the guinea pigs than Ecotope has been in the past. So it's good to make sure there's systems out there that are actually working to demonstrate that what you put all this money and time into will actually make hot water as you intend. And here's some resources for further guidance. I pointed to a couple of these resources already. One that I haven't pointed to is this design guide, this for Energy Trust of Oregon. It goes through these different temperature maintenance configurations, single pass and multi pass, and quite a few other things like heat pump locations and mounting. And then here's the further links to the advanced water heating spec and Seattle City Light incentives. Uh, Building America Solution Center is coming out with more really high level heat pump guidance, and that's not out yet, so I can't provide a link. But the probably the most one of the most important things here is there are no dumb questions to your manufacturer. So make sure you open a conversation with your manufacturer, your rep, if you're going to implement one of these, and take them through the advanced water heating spec and through these slides, and point to different things and make sure that they're up to speed on providing the right guidance to align with what I've talked about today. So this is the final check-in before the thank you slide. So if anyone is staying longer, I think I can, we're past time, but I can definitely answer a couple of those questions that I may have skipped earlier. Um, but Katie, is that, I don't know how overages work
Yeah.
with playing Design Lab. Are you cool with
We're
staying
kind of
on?
fluid. Yeah, yeah, there are still several people on. I mean, don't feel bad if your question didn't get asked. Many of you were curious today. I don't know, do you want to go through the remaining ones, or should we just let people have lunch?
Yeah, yeah, give me a few awkward seconds to scroll through
Sure.
some of these questions. Um,
And this is all recorded, so if you do have to drop off, you'll be able to hear these questions later if you go find the recording.
yeah, I think these we were a lot lighter on we were a lot lighter on questions on the last slides. I know I sped through those pretty quickly, but I wanted to take a lot of time on like the really fundamental way these heat pumps operate and as they pair to their storage and things. So I hope people got a lot of value out of this. I think one question that I'll definitely be Googling later is a quick comparison on CCE versus UEF. I On the commercial side, we've dealt with heat pump COP, coefficient of performance, and system COP pretty exclusively. I'm pretty familiar with UEF, uniform energy factor, but not familiar with CCE. So I will be I will be researching that later and hopefully have an answer, but don't have it now. Um, but yeah, I think let's see. Oh, that is a good one. So are most of these systems manufactured in the USA or outside of the USA? So there are a lot of there have been a couple of US manufacturers around for the last, man, two have been around since the 80s selling equipment in Hawaii. And then there's a lot more US manufacturers that have made other equipment that are large manufacturers that are are moving to heat pump water heaters because they see the value here. So it's really exciting to see the market expanding. But there are also foreign manufacturers coming in because they now see the value in the US market. So we have, I won't name any manufacturers specifically, but we do have several both foreign and domestic manufacturers of these heat pumps with CO2 refrigerants and non CO2 refrigerants, like the new synthetic blends that are coming out for slightly lower GWPs. So yeah, I think that was kind of the big question that were most that was most recent. And so I think I'll leave it there, and
Cool.
I'll go to my thank you slide. I do have an email that you can reach out to me if there's stuff you want to work on. I love diving in the weeds, as you might have noticed. But with that, I think that's all I have today.
Okay, I think that's good enough for today, Evan. That's a lot. That was a great presentation. Thank you, everybody, for coming and sticking in with us here the last few minutes. Again, it was recorded, so you'll be able to review all this information at like 0.75 speed if you need to. Um, and I hope everybody has a great afternoon. Thank you again.
Yeah, thanks everyone. Thanks for hosting me, Katie.
Sure, thanks, Evan.